Now we're going to study exponential growth and decay. So first, exponential growth. You may have heard the term from someone out in the real world. Something was growing exponentially, and they meant it was growing very fast. So remember the two functions we looked at previously. Y equal 2 times x, which graphed, of course, is a straight line, and that was a constant rate of change. But then in this chapter we looked at y equal 2 to the x, an exponential function, where x, the exponent, becomes the variable. And we saw that it started out pretty slowly, but then it got faster, a lot bigger. So what we're going to start with now is what you see here, the definition. A quantity is growing exponentially if it increases by the same percent in a unit of time. And this is exponential growth. So we're going to look at some real-life examples. So let's look at this money example. You deposit $500 in an account that pays 8% annual interest compounded yearly. What's the account balance after 6 years? So you start with $500 and have your calculator ready. Hit pause if you don't have it out. So you're going to start with $500. That's the beginning of the first year, but you get to add to that 8% of $500 throughout the year, and by the end of the year, calculate that, what would you have? So you'd have $540. So now to start the second year, and this is what it means by compounded yearly, that you're going to start with $540. Okay, and again, to that you get to add 8% of 540. Again, calculate that, and you'll get about $583.20. So hit pause, continue to do that, and go up through 6 years. So in the 6th year, you should have gotten that you ended up with $793.44, or at least it rounds to that in dollars and cents. So again, what we did here is I kept changing the starting value. There's another way to look at this using exponents. We've seen this idea before when we started with a bill and we added on the tax. So if you look at the $500 that we started with and then adding 8% of that 500, remember another way that we wrote that was you could just say that's 108% of the original 500. So what you see here is that the first amount at the end of the first year, that 540, would come from 500 times 1.08, but then the second year you could recognize that that 500 times 108 is the starting value of the second year, and then it's times another 108. At the beginning of the third year, you would have had that 500 times 108 once, and then times 108 a second time, and come up with that 620, and then times another 1.08, and you'd get that 629 and about 86 cents. So again, we can look at that. If you look at that pattern there, you see that 1.08 one time, 2 times, 3 times, and again all the way up to in the 6th year it would be 6 times. So that's a way to write that exponentially, which means that we could write a formula for this and not have to go through the second time, third time, fourth time, but just go right to the 6th time if that's what we were looking for. So here's the formula, or that exponential growth model. So if you look in blue, C is that initial amount. In our money example, it was $500. And then that 1 represents just getting the initial amount back again, and then plus whatever the rate of increase is going to be. That R is called the growth rate. So ours was 8% growth rate. And then the T in red there is the time period. So in this last example, if we want to find the amount, and again they're using Y, feel free to use A for amount, we could just take the $500, we could multiply by the 1 plus 8%, which would be 1.08, and in this case we wanted to take it to the 6th power. So put that into your calculator. and you'll see that you get exactly that same result. So this is what you should have entered into your calculator, that $500, the left parentheses, 1.08, and then close the parentheses, make sure, and then caret to the 6th power, and you should have gotten about $793.44. So if you look at the graph here, it doesn't look like it's a very fast increase, and I was talking about the exponential growth being fast, but what happens, it depends on the percent rate, it depends on the initial value. So 8% is fairly small, and eventually you would see a large increase, but it takes a lot of years. That's why they say even if you have a little money invested, but you won't see a whole lot until down the road. So you want to start putting some away and letting it grow for you. Also, 8% is very high for right now. Banks aren't giving anything close to that right now. So the money's growing even slower than this. Okay, now you're going to try one on your own. So here's the problem. Again, even before you read it, I'm just going to write the formula, and then you're going to hit pause and copy everything down. So either the amount that you end up with, or you can call that y, you're going to have your initial amount, which is referred to as c, 1 plus whatever the rate of increase is, close the parentheses to the t power. So hit pause and take that down and work out the problem. You should have gotten about $245.68. Again, make sure that for your percent, so you've got the 200, make sure you're at 1.042 and close the parentheses to the 5th power. Here's a different kind of exponential growth problem. Population of 20 rabbits is released into a wildlife region. Population triples each year for 5 years. What's the percent increase each year? So we can still look at that. I'm going to use P for population, and the initial amount we start with is 20. But now, if we look at that growth factor, which remember was 1 plus R, well, the 1 meant getting the initial value back again, so that 1 would give us the 20 back. But then if it gets tripled, there's an extra 200%. So that would be, there's your 1 plus 2, which is the 3. It's getting tripled, and then it's 2 for 5 years. It triples each year for 5 years. So the percent increase after each year is that 200%. The growth factor is a 3. You're tripling. So just be careful, that 1 that's always in that formula still has to be in the formula if you're looking for the percent increase. It's the extra 200 that's the percent increase. So do this one and get the population after 5 years. Remember to hit pause when you need to work out a problem. So you should have gotten 4,860 rabbits after 5 years. I don't know if anyone's ever had rabbits as pets, but they do tend to multiply very fast. So hit pause if you need to go back through this and review that growth rate and the growth factor. The growth factor is 3, the growth rate is 2, which comes from that 200%. So here you see the graph, and you can see that exponential is growing very fast. It really comes into play here. Hit pause if you need to look at this more. Now look at this graph and decide which model, A, B, or C here, best represents the growth curve shown. So there's a few things you need to think about. So again, remember, you've got the first x value there is 0, and what's anything to the 0 power? So all of those parentheses to the 0 should end up being 1, right? So you can eliminate immediately choice C, because at 0, the y value is 100, not 200. And now, how would you decide which of the other two fits better? So hopefully you thought about putting in a value. So if you look at, let's say you're going to plug in 2 for x, so the 1.2 squared would be 1.4 1.44, but the 1.08 squared would be about 1.66. Sorry, 1.166. So now look at the graph. When x is 2, if you look up, it reads like it's about 150, maybe a little bit short of that. Again, remember, we're going to take the value times 100. So it certainly looks like the 1.44 fits that better than the 1.16. So that's what you do. You just analyze the input values and check out what the output values are. So in this case, we're going to choose B. Exponential decay functions are very similar, as you can probably guess. Just instead of growing, they're going to be getting smaller. So growing exponentially, remember, increased at the same percent each unit of time, but a quantity that's decreasing exponentially decreases by the same percent. And this is called exponential decay. So if you look at the model there, the only difference is in the parentheses. Instead of 1 plus r, we've got 1 minus r. Again, that 1 minus r is the decay factor, and the r is the decay rate. So when will it decay? Well, you're taking something away from 1, so we need to make sure that the r is between 0 and 1, so we don't get a negative there, or you'll get that fluctuating back and forth kind of thing. So you're just going to look at what's in the parentheses in any type of formula like this and make sure that it falls between 0 and 1. Then it will be exponential decay. Here's an exponential decay problem. From 1982 through 97, the purchasing power of $1 decreased by about 3.5% per year. Using 1982 as the base for comparison, what was the purchasing power of $1 in 1997? Okay, so if you look at the solution, again, we're going to start with our decay formula. Y equals the initial amount, 1 minus r to the t. So the initial amount this time is just $1, and the decay rate is 3.5%, so of course you see the 0.035. And then we want the purchasing power in 1997, which is 15 years from t equal to 0. So again, in this time, because you're multiplying by 1, of course you can just deal with the parentheses and the power t, so 0.965. And then you just put in 15 for t and punch it on your calculator, and you get about 59 cents. So it lost that much, 41 cents. So hit pause and try this problem. So the decay model you should have gotten is this, your 18,000 times the 0.88 to the t power, and then after 8 years you should have gotten about $6,473. That's what your car would be worth in 8 years if you started with 18,000. If you did this the long way on the calculator, the way we did that investment before, you'd see this kind of a thing and still get the same answer, of course, a little more time consuming. And the graph of a decay model, of course, is going to be going down. So you see at time 0, where the parentheses drops out and becomes 1, you see that initial value, of course, is the starting place, and then it decreases here. So sometimes you're just trying to determine if something's exponential, growth, or decay, and that's pretty easy. Just look inside the parentheses. It's bigger than 1, it's growth, that 1 plus r. If it's between 0 and 1, then it's decay, like the 3/5 here. So B, of course, is decay and A is growth. Here's the graph of both of those, and that 1.2, that growth, of course, the 0.2 was the extra, so that's a 20% rate of increase. Otherwise, if it were 2%, of course, it'd be 0.02. And then the 3/5, the decay, is 1 minus r, remember, so that would have been 1 minus 2/5, and 2/5 is 0.4 or 40%. So that would be the rate of decrease. So here are the standard exponential growth and decay models with all the values we talked about. Notice both graphs have that 0 c value when t is equal to 0. Right? Then you have the parentheses to the 0 power. Anything to the 0 power is 1, so you just get c. So just take a look at that and make sure you're really comfortable with those formulas. So for your model, you should have gotten that the value of the business, Y, was that initial value of $85,000 times 1 minus 0.02, for the 2%, to the t power. Or, of course, you can write that as 85,000 times 0.98 to the t power. And then you should have gotten, after 10 years, about $69,451 for the value of the business. So take a moment to look at the graph and then the choices for the model that would fit that graph. Decide which A, B, or C, which one you think is correct. So hopefully you eliminated B right away, right? Because it's growth and not decay. And it's always kind of nice and easy when you can check a 1 and pretty clearly see it. In this case, if t were equal to 1, right, the 60 times 0.8 would be 48. Again, that's for t equal to 1. And same thing for C. If you just plugged in a 1, you'd get the 60 times 0.4, which is 24. So all you really have to do is look at the graph for t equal to 1 and see that value that we see there. Is it closer to 24 or 48? Of course, it's closer to 24, so C is the correct answer.